So today we're covering polynomial functions. Those are the pages in your text, and we're into chapter 3 already. So a polynomial of degree n, that n is going to become important in a bit to kind of start graphing some of these and visualizing what they might look like. It's just a function of this form, okay? And this form maybe looks a little intimidating right now just because there's a lot of terms and there's these like subscripts and a lot of letters. But basically what's going on is you've seen many forms of polynomials before, okay? So let me put up a couple examples and then try to indicate why this form has to be this way, why this is the best way to define what a polynomial is. So an example is any quadratic function that we've done before. So quadratics take the form ax squared plus bx plus c. Okay, so in this instance, we use letters to represent the coefficients, a, b, c. The problem with doing that in general is eventually you run out of English letters, right? We can go a, b, c all the way to z, but what happens if we need another term, okay? So that's why these subscripts, that's why numbers have this power. By using these subscripts, we're never going to run out of numbers the same way we would run out of letters. So this is an example of a polynomial of degree 2. 2 is the highest power of x represented in this function. So when we say of degree n, we're looking for the highest power, okay? Let's look at just a few more examples to know that they could take vastly different forms. So maybe we have a fractional coefficient times an x plus another fractional coefficient times x to a different power. It's okay to kind of skip some of these powers, right? That's x to the first, if it's not written, the exponent's 1, and that's x to the fifth. It's okay that I skipped squares, cubes, and fourth powers. That's just indicating in the form that some of these coefficients are actually 0. That's all right. If I look for the highest power of x, that's going to tell me the degree. Degree there is 5. So there's 2 examples, and then we can also have what's called a constant function. So here, no x's at all, right? Just the function is always 5. That would be a nice horizontal line at y equals 5. So there's no x's here, so we can think about this as x to the 0 power. X to the 0 power represents the number 1. So if that's not written, we can still think about that as being implied, and that's a function with degree 0. Okay, so these are all examples. It's also helpful, we've done this before, to look at things that are not examples, right? To kind of distinguish what makes a polynomial different from other types of functions, and maybe to prep us for some future work that we might have to do. So some non-examples. So here's a function, I'm calling it k. K is 1 over x, which we have graphed before. We did this for translations, and we looked at the domain and the range and maybe moved it around a little bit. But that does not take this form. It does not have the form of x to a positive power. All of these powers are positive. 1, 2, 3, 4, 5, 6, 7, all the way to 9. That's not a polynomial. We can also have different types of functions like trig functions, sine of x, which we're going to learn about during like the last few weeks of the course. That's not a polynomial. That has different properties. Another function that we'll learn about later in this course is 2 to the x, and we'll call that an exponential function because x is in the exponent. That's not of the form of a polynomial. A polynomial is supposed to have x raised to a numerical power, not a number raised to a variable power. So these are all non-examples, but we'll cover things like that later in the course. Okay, so in looking at some of these functions, we next want to start talking about some of their properties. And one of the first properties we're going to talk about is their graph, right? How do we visualize these? What makes a polynomial different from other types of functions that we've covered? Okay, so let me create some space. And some of these we've already done before. So we've already graphed the function y equals x. So that's a line with slope 1, y-intercept 0, right? Just x means the coefficient's 1, and the y-intercept is 0, not given. We've also graphed y equals x squared. Parabola opening up with a vertex at the origin. We've graphed y equals x cubed. We had to do this for the translations worksheet. Takes the following form. Newer ones, notice I'm just upping the power of x, x to the first, x to the second, x to the third. So this next one I'm going to look at what does x to the fourth look like. We can graph it in Desmos. It looks sort of like a parabola, so it looks a lot like x squared, but it's a little bit wider at the origin and a little bit steeper up past the origin. So steeper up here, wider down here. Y equals x to the fifth. It's going to look a lot like the shape of x cubed, but again, it's going to be wider through the origin and steeper past the origin. Okay, these are rough sketches, but of course we could do it with software if you wanted to look at them in more detail. So in general, let's make some generalizations built on what kind of patterns we might be seeing here. So in general, if n, the degree, is odd. Okay, so let's look at the odd ones. X to the first, cubed, fifth. Okay, so these are all odd degree. If n is odd, then we have some similar properties. One thing that's happening here is as x goes big and positive. Okay, so this is new notation, but I just have x arrow infinity sign. So I'm saying x not equal to infinity, but x is getting closer to infinity. X is big, positive numbers. So if x is big and positive, what happens here is the y values also get big and positive for these graphs. So up here, x is big and positive, so is y. Big positive x, big positive y. Big positive x, big positive y. And let's look at the reverse sign. What about as x is big but negative? Okay, so think about where big negatives are. They're over here, they're on the left side of the graph. Well, what's happening to those y values? X is big and negative. What's going on to the y value? X big negative, what's going on with the y value? Well, the y values are also going big and negative as well. Okay. Third point I want to make from this graph is what's happening in the middle. Not on the extremes, not this end behavior, the infinities, but what's happening in the middle. What's happening in the middle? What's happening in the middle? So I'll say that the graph crosses at the origin. Meaning the graph starts below the x-axis and then crosses, and now it's above the x-axis. Below and then above, below and then above, and that cross happens exactly at the origin. Okay, I want to build similar generalizations for n being even. So capture this already if you haven't, and I'm just going to expedite it and say, okay, if n is even, well then I'm talking about 2, 4, and I could draw graphs for 6 and 8 and look at all of them together, but they're going to look very similar to these two. So big positive x, so I'm over here on the right, what's happening to the y? Y is also big positive. What about big negative x? What's happening to the y? Well, the y is not down this time, it's up. So the y values are also big and positive. So I made this edit here from our previous generalizations. Okay, and the graph is not crossing the x-axis. It's staying above the x-axis. Staying above the x-axis, staying above the x-axis. So I don't want to use the word crosses at the x-axis. I like to think about it like a bounce. Like I'm going to come down, I'm going to hit the origin and then bounce right back up. Sort of like it's the ground. I'm like tossing a ball. Okay, right? I bounce, comes right back up. Doesn't go below the ground. So the graph crosses at the origin. So if you need to capture this generalization for even functions, just go ahead and pause the video and you can record that important information. Just as a reminder of how things could change or how we could connect this to previously learned material. If we're looking at a negative sign. Is going to reflect the graph across the x-axis. So if, as an example, I want to look at negative x cubed, and that end behavior we talked about is now going to be reversed. Instead of big positive x being big positive y, I'm going to have big negative y because of that reflection. And instead of big negative x being a big negative y, big negative x is going to be big positive y. And I'll have this type of shape. So I just want us to be aware that translations are still going to apply here. Negative signs are going to force us to sort of have some opposite relationships that we have to concern ourselves with. Okay? All right. These are for very basic functions, right? This is just x cubed, no other terms. X squared, no other terms. I want to end the video with an example of a more complicated function. So I want to graph the function x cubed plus x squared minus 4x minus 4. Okay, now I know I could, of course, plug this into a graphic calculator or some sort of software, but let's see if we can use some of our previous knowledge to understand what's going on. I see the degree is 3, okay? So I already kind of know the general shape of this graph. I know that I'm going to have sort of the same end behavior that the x cubed graph had. So the x cubed graph was big negative x was big negative y, big positive x related to big positive y, okay? But I don't know what's going on in the middle because I have these extra terms here. So I'm going to start by finding the zeros, or we've been calling them x-intercepts. X-intercepts occur when y is 0. We've had that as a fact, and we're going to continue using that. So if I set this whole equation equal to 0, and then I have to make an attempt to solve this equation. All right, back in video 1, we did talk about how we could factor when we have 4 terms. Doesn't always work, but we need to at least try it. I don't have another method. I can't use quadratic formula. This is not quadratic, it's cubic because of the 3 power in there. So if I'm thinking about factoring, I group together the first 2 terms. I think about just those first 2, ignore the last 2. What do they share? What do they have in common? Oh, they share an x squared. If I factor that out of the x cubed, I have an x. Factor out of the x squared, I'm left with the plus 1. Okay? Similarly, the next 2 terms, what do they share? What do they have in common? Well, they're both negative, and they both have a 4. So I can factor out a negative 4 from both terms. Again, ignoring those, just looking at them in terms of pairs. So if I take out a negative 4 from the first term here, I'm left with a factor of x. If I remove a negative 4 from a negative 4, I'm left with a positive 1. Factoring is like division. So I'm thinking about, I started with negative 4, but I needed to divide by negative 4, and I'm left with a positive 1. So factoring is like division. Now what I've got going on for us is the exact same term appearing twice. The exact same factor. There's an x plus 1, there's another x plus 1. So if I view this as continued factoring, I'm going to factor out the x plus 1 from the first term. So if the x plus 1 is no longer there, it's factored out, I'm left with an x squared. From the second term, I'm still factoring out the x plus 1. If it's no longer there, it's been factored out, I'm left with a minus 4. And that's called factoring by grouping. Still equal to 0, still equal to 0, and I see that there's more I can do. X squared minus 4, I can factor further as a difference of squares. X squared is a square, 4 is a square. So I can write this as x minus 2, x plus 2. Okay, almost had a little error there. Now that it's factored, I can set each factor equal to 0. So if the first factor equals 0, there's one possible x-intercept. Second factor equal to 0. There's a second x-intercept. Third factor equal to 0. You don't have to show all this work if you're doing mental arithmetic. That's fine. Those are my x-intercepts. I'm ready to start building this graph. Okay. X-intercepts at -2, -1, and +2. Let me label. All right. And I still know that I have this same end behavior. So the graph ends up here and sort of begins down here. It might be helpful at this point to also think about the y-intercept. A function's only ever going to have one y-intercept. Y-intercepts occur when x is equal to 0. So if I plug in 0 to the function, 0, 0, 0 minus 4, it's pretty simple to find a y-intercept. It's much more complicated to find those x-intercepts. I have a y-intercept at -4. Okay. Now I got to play connect the dots in some sort of a way. So I know my end behavior. I know I've got to go through all the intercepts, and I go through them in order, right? I'm not going to go through this one first and then track back. Functions can't work that way. I can't go backwards. So I come up here. I just need to pass through all of my dots and try to connect my lines. So obviously I didn't make a perfect drawing here, but I'm going to call this a sketch, right? This is not perfection. Questions you might have is, well, how high do I make this hump, right? Is it way up here? Is it maybe a little bit more shallow? That's actually something you're going to learn in calculus. We're not going to cover that here in pre-calculus. We're just going to get this general shape, and then when we want to talk details, you might be doing that next semester if you have to move on to calculus class. So knowing how high or how low some of these peaks and valleys are is not a pre-calculus topic, but just getting the shape right is. Okay? All right. Good luck on next videos or homework assignments. Continue to post questions to this video if you've got them, and either I will answer or maybe a classmate will answer. All right.